Hey, hi, I'm Dan Barabee, and I am attempting to explain the ins and outs of photovoltaics as they stand up here in the northern latitudes. I'm located here in Anchorage, Alaska, and been working mostly in weatherization for the last 35, 40 years. But my original training back in the early 80s was in solar design and construction and passive solar building and active solar systems. So here we are many years later, and I'm finally getting to do a real installation with PV cells. For me, it's as much an education process as it is for everybody that might be watching this. As you know, this is being produced for a virtual conference with the Energy Out West organization that was going to be in Austin, Texas. And I was going to be doing a little PV solar water demo there in the classroom, and then we were going to put them outside up near the swimming pool. But this is not what's happening. And so here I am in the heart of Anchorage, Alaska, my hometown, and I am going to go through the ins and outs of both grid tie and off-grid systems. So one thing I'd like to say before launching into this is a demonstration project. It's educational purposes only. I can't hold total responsibility for any of it. So this is what we refer to as the rack for the PV panels to set on. Depending on your application, you might have a more sophisticated setup, but being that we're using the angle of the roof as our angle to the sun, we're able to mount these right to the roof, and we're hitting onto all our rafters. And the setup is basically just a common material, just a unistrut that's a 2x2 mounted to our standoff brackets, which are specially made for solar, and then our fasteners that then hook right into our unistrut and then fasten down. This whole setup is probably, for this roof, is maybe around $80 in materials. And it seems plenty strong. It allows snow and water to pass underneath, and it should last a long time. In case anybody's wondering, I've set the panels at 53 degrees angle, which is pretty good to the sun. The thing about Alaska, you'll see a lot of panels mounted vertically so that you never have snow collecting on them, and you still get a pretty good return on an annual basis. We're going with this angle just because it was pre-existing, and it should be enough angle to shed the snow. And I think we'll go ahead. So we've got room here. Okay, so let's go ahead with our first panel. There we go. How does a PV cell work? Here you can see this is just one cell, one thin cell, 1/64 of an inch thick, and it's made out of silica, same material that glass is made out of. Very fragile in this state because it's not mounted to anything, and it is producing electricity as I hold it because I've got light. It takes light to make electricity with a photovoltaic. You can see, if you look closely, there's these bits of what look like metal bar, and then on the back there's also some metal strips. Those are the contacts for both the incoming and outgoing electricity. If I take you over here to the graphic, which is basically a cutaway view of a photovoltaic, it's basically two layers. There's the top layer, which is the N-type silicon, which has phosphorus doped onto it, And then on the bottom is the P-type silicone, which is boron doped. The top layer is positive, the bottom layer is negative. In between, there's a junction. So nothing happens in the static state. But as soon as the sun's rays strike onto the surface of our PV, we start making electricity. It starts pushing electrons out of the positive field and they move to the negative field, creating a current, creating electricity. At that point, that electricity then can be utilized, moved out from the bottom contacts to whatever our load might be, and returned back to the top contacts. It's a very simple, elegant process with no moving parts. All we need is that beautiful sun 93 million miles away bombarding the Earth with photons. So here we have our little cell, one PV cell, and I'm putting my contacts of my multimeter on both the positive and negative, and you can see sitting here, not even in direct sunlight, we are making almost a half a volt of electricity. Okay, so this is a fairly typical panel. It is individual cells, and if you were to take the time to count, you'd see there's 60 cells here. And this panel puts out 31 volts. So each little cell connected to the next one and the next one is about a half a volt per cell. So if you look at the model number on the back, it will actually tell you that it's a 60 cell panel. We are hooking these panels up in series, so essentially meaning that we're going negative to positive between each panel. Basically, with every connection on a series, you increase the voltage by the voltage of the panel. So with 4 panels at 31 volts per panel, at the end we're over 120 volts, like 124 volts. So per kilowatt now with a panel has come down. Probably 20 years ago we were looking at least $4 a watt. Now we're down below $1. These are coming in probably around 65 cents per watt. So there you go. It's becoming more and more cost effective, even in Alaska. The first thing you really need to think about is your access to the sun. If you are considering putting up any sort of solar installation, PV panels, you need to take a look at where you're going to put them. And a lot of that depends on where you're located on the planet and where you're located in your neighborhood and where you're located. Your roof, is it pointing south, and what is the angle, and what is the obstructions in front of that roof, and will there be future obstructions if you do decide to put your panels in a certain location. So it's kind of a critical aspect that you have some control over, but not total control over. For instance, even in this property, we had a big tree that recently died because of a spruce beetle infestation and has been removed. So now we are getting more sun onto our panels. It was kind of maybe the positive, aspect of losing the tree. The negative is we lost a tree. Okay, so here we have a sun chart that is for this exact location. We're at latitude 61, and essentially what it's showing us, see, maybe I have a pointer here, be able to show you a little more clear. You can see these blue lines represent different dates of the year, and that's the path of the sun. And these other lines, the red lines, are representing the solar time. So as you can see, for us in December, our sun is very low in the horizon. That might be more obstruction than when it's higher in the sky in the middle of summer. Say, this point here would be the solstice, noon in the summer, and we're at about 53 degrees in the sky. So not super high, but we are in the far north latitudes. But this gives us a very good ability to take a look at our site and be able to tell how high in the sky the sun will pass at different times of the year. December, November, October, September. Here's August, July, and then June. And it would reverse itself for the spring equinox months. So that gives us something to work with. Now, in the old days, when we first were doing site analysis, we would have a clear mylar, and we would take that same chart and we would bring it out with a compass, and we would view the sky and see basically what obstructions we might have. Here's an example of a satellite image of this exact property, and then you see right here, that's the location of the PV cell panels. Those are pointed south, and it gives me basically my system capacity based on that location. That was all done on the internet on the NREL site, the National Renewable Energy Labs. They have a free site you can go on. You plug in your address and tell them what size your PV cell array is going to be and its direction it's facing, etc., and it will give you a fairly good estimate of your potential. Here's the actual results based on everything I plugged in. You can see here's the system specifications, the 1.2 kW system, standard. Its array type is just fixed, meaning that it doesn't track, it's just a fixed location. You've got your array tilt at 56 degrees. You're pointing due south at 180 degrees. System losses 14%. And since I don't have an inverter, I was able to put 99% in there. And then when you look up here, it's going to give you your actual estimate for your annual solar radiation and the amount of actual energy that you will produce over an annual period of time. It's estimating me to be able to produce 1,354 kilowatt hours per year. That equates to about $271 annually. Now that makes me think that maybe in less than 4 years this system is going to pay for itself just in electrical savings. You can also notice how our collection of sun varies quite a bit from January to, say, June or July. We go from less than 1 kilowatt hour per meter square per day down to June and July almost 6, 5.7, 5.72, and so there is a big variation for us from winter to summer. But that's a pretty nice tool that's available to anybody, and it's free, and it's very intuitive, easy to use. So I'd like to talk a little bit about the different types of systems that we usually see using PV solar. And basically, we've got on-grid, we've got off-grid, and we've got hybrid. So if we talk off-grid, I'll show you just a bit of a schematic here. The main thing about an off-grid system is that you are not hooked to any grid power. You are your own power company. You're producing your own power. And one of the bigger factors with producing your own power is having power 24 hours a day, or being able to collect your electricity when the sun's shining, but also have a way to stretch that out, say through the night or through shady days or dark days. So that's usually where most of your off-grid systems will have a battery bank. And so you'll charge that with a charge controller. The beauty of that is you are your own power company. sort of the ugliness of it is it's an expensive system when you're talking battery banks. A lot of times in Alaska, we have to also supplement that battery bank in the darker times of the year with some type of optional generator, which could be diesel, could be gas. Another option with a system such as this, maybe you have solar panels and you also live in a windy area. Maybe you don't have much sun at certain times of the year, but you'll be creating electricity using the wind. And you also are going to have a component, the inverter, which is going to take that DC power either from the sun or from your battery bank, run it through the inverter and create your AC power, which then would be able to use any type of AC type appliance you're wiring, standard wiring in a house. So that's your basic off-grid system. Then we have what's called more of the grid tie or the net metering system. This is going to be your solar panels, and then they're going to go through an inverter system that is going to take your DC electricity and convert it to AC and essentially turn your meter backwards when you're producing electricity, or feeding it directly to the house from your inverter and utilizing it for your daily load in the house. If you're making more electricity than you're using, then you're turning your meter backwards. On the days you don't have sun, you're going to be pulling out of the grid back through your meter into the house. So essentially your utility grid is your battery. This is probably one of the more popular systems because it's easy to set up. There is a certain expense involved just to have the proper connections. You're going to need a disconnect. I have a little better setup over here that shows a switchboard that you would be able to, if ever this system failed, you would be able to disconnect it from your meter box. If ever the power grid was to have a power outage, this also is going to turn off any power, because the last thing you want to do is feed power into the power grid when there's a problem and they think they have it turned off. So the other system, which is kind of in between, would be a hybrid system. And this you see more these days for people that want to have reliable power even if there is a power outage with the grid. And the other beauty of this is in some utilities there's what is called a demand charge for higher demand times of the day. And this might be, say, later in the afternoon when everybody comes home and turns on their air conditioning, for instance. And all of a sudden the utility company is strapped to be able to meet that demand. So they will charge more for that electricity. So we've heard of the Tesla battery system and some of these other battery banks. They're really a kind of a standby battery bank, not necessarily to run your whole house on for a long time, but if you've been generating electricity during the off-peak time during the day when most people are off working, you're banking that electricity in your battery bank. When it does come to the peak time, you're able to switch over and use your battery bank to run your inverter, so you're not pulling any electricity through the grid and through your meter. So essentially saving money by avoiding demand charge. That is basically what a hybrid system is. Now we're calling our hot water heater system a hybrid system because we're using both AC and DC. With this particular system that I've designed, I'm not having a grid tie or battery system. I'm basically using water storage in the water tank as my battery. Water has basically a coefficient of 1. Everything else is based on the thermal storage capacity of water. So essentially we've got a battery that is made up of, the most prevalent liquid on Earth, water. Now we're talking about an on-grid or different types of hookups. Let's head on over to a large photovoltaic panels set up on a multi-family, multi-use building with a housing authority here in the neighborhood.
I'm Sean Holdridge with Cook Inlet Housing Authority. I'm the Building Systems and Energy Sustainability Manager. Cook Inlet Housing Authority's mission is to create housing opportunities that empower our people and build our community. Two important takeaways from that is that basically we serve everyone. We don't exclusively serve a certain group of people. The second important thing is that building our community, we are an affordable housing provider. However, we think of ourselves more as a community developer. We go into a community and try to be the catalyst that'll make that community grow and bring other businesses in, parks and infrastructure. So we stumbled into solar photovoltaic. Most of our developments, if not all of them, are funded through the Low Income Tax Credit Program, which is administered by AHFC. And they started giving points to incorporate alternative energy systems in your development. So of course, points is the name of the game, so you get funded and you can build your development. And so all of the developers started incorporating alternative energy. Once we started getting some systems in our developments, we quickly realized that it's helping lower our operation costs, and the obvious reason it's good for the earth as well. So when you drive around Anchorage, you're going to see alternative energy on all of our buildings. We hope to have it soon on our main office building. In this particular building, we have a 18.5 kilowatt solar photovoltaic system. We have solar thermal in some of our developments, solar PV, and then we also have geothermal. And we've found that the solar PV makes the most sense here in Anchorage. The cost of electricity, we pay roughly 20 cents a kilowatt hour, so anytime we can reduce our electrical loads, that benefits us operationally as well as our residents because we can keep the rents low. We have roughly 350 kilowatts of solar PV on our developments. So we cover the whole Siri region, which generally runs from Seldovia up to Cantwell. In addition to the alternative energy systems we have on our developments, we also build to a very high standard in construction, and our buildings are super efficient. We use LEDs throughout the building. We over-insulate. We do a lot of air sealing. Our buildings generally 1 to 2 air changes per hour. And so when you have a very efficient building like that, that just helps with your alternative energy system. You're getting more bang for the buck. So I've been a project manager for 27 years, and this position that I'm in now is rewarding in a different way than being a project manager. And what I mean in that is that I get to track all of the energy that we're producing and seeing what it offsets and how it helps our costs, our operational costs, and just the benefit that it has, for the earth. So last year we monitored 8 of our developments, which has roughly 136 kW of solar PV. And in 2019, we produced 110,000 kilowatt hours of energy. Super fabulous. Our typical installed cost for our solar PV is somewhere in the neighborhood of $3 a watt, which is roughly $3,000 a kilowatt. Recently, we've been toying around ways to get those costs down. So when you drive around Anchorage, you're going to see panels on the face of the building versus on the roof where we have these large structural frames to hold the racking. And so we're seeing our costs go down when we're on the face of the buildings. And so what we did next is we started analyzing production, versus the roof versus the walls. What's interesting about the wall panels is they don't get snow on them in the winter. And our sun angle tends to be lower in the winter, so they're hitting the panels better than the ones on the roof that are covered in snow. So I think going forward, you're going to see our developments have both styles, roof and wall panels.
Okay, we're back at the shack and talking about the difference between AC power and DC power. The PV cells produce a DC power, direct current, meaning that it just goes from positive to negative. AC current is an alternating current. It goes from positive to negative 60 times every second in a standard utility-tied AC system. Why AC? Well, AC is easy to meter. Because of the alternating current, they can tell exactly how many watts you're using at any given time, and you can pay for it very easily. With a DC current, it's not so easy to do. But the beauty of a DC current is that it is what PV produces. A lot of grid tie systems will actually have to have an inverter that then will take that DC and convert it to AC. Our PV panel array is producing DC power. That will then get optimized through the MPPT controller onto a 30-gallon electric hot water tank. The electricity produced will then get utilized by the load. In this case, the bottom heating element of the tank. In a typical electric water heater setup, there are two elements that go through thermostat controls and are wired in parallel. The top element is heated first. The bottom element is turned on after the top element reaches the set temperature. Both elements are never on at the same time. The top element is heating the delivery water, and the bottom is heating the standby water. This particular system has the bottom element producing heat from the PV panel array, and the top element utilizing AC from the utility. The bottom element is completely disconnected from the original controls in the AC power and will be controlled by the MPPT with a temperature probe at the bottom of the tank set to a temperature of around 160 degrees. On a good sunny day, we should be able to heat the water in the tank a significant amount and reduce the amount of power being drawn from the grid for the top element. This thermostat on the top is often set a little higher than the bottom element. Now let me explain AC versus DC. DC is direct current, meaning that it goes from positive to negative. It just continually flows from positive to negative. AC is an alternating current. It goes positive to negative every second 60 times. So that's a 60 hertz standard system in the US. That meter is able to read the current flow because of the alteration, the alternating amount. So then you're able to be billed for your electricity very easily. And it would be the same if you were selling electricity back to the utility. So bottom line is our DC, when the sun's out and we're producing electricity, we're going to be producing heat. How much? We're not sure yet. Remember, this is a demo. I've never done this, and I don't know if anybody else has done it in Anchorage. One thing that is often done with systems that are off-grid, they would call this either a diversion load or a dump load. Say you've got a standard off-grid system with batteries. Your batteries get completely charged with a sunny day. What are you going to do with that electricity that you're still producing? If you're a grid tie, you could sell it back to utility. But because you're your own utility, your own power company, you're still producing power, you're just going to let it go to waste? No, you could actually use that excess power and do what is called a dump or diversion, and you'll send that extra electricity and heat this element. For this system, as a demo, we are just going to use our water tank is essentially our battery. We have no other backup. It's going to continually just heat that hot water as much as it can in a day and hopefully put less demand on that top element for heating the water to delivery temperature. With monitoring and a look at temperatures and how much AC is going into the top element and how many amps we're producing on the bottom element, we should be able to monitor this and see how cost effective it actually is. The benefit of AC over DC is that it can be transmitted at higher voltages and smaller diameter wires. You start getting DC over a long period of or a long space of distance, and you need very large wires to be able to conduct that DC electricity. Now, a part of history, as we all know, the great inventor Edison, well, one of his workers was Tesla. And Edison had worked in the late 1800s to come up with basically a way to supply power to people. It was in New York, and he had a grid set up using DC, but it was low voltage, and he wasn't able to send that electricity much more than a half a mile to people's homes, but they were the first people to be electrified, and they had electric lights and some simple appliances that would run off electricity. Maybe a toaster, I'm not sure. But there became a battle starting. There was going to be the World's Fair of 1883. And Tesla came up saying, well, AC makes more sense because with a transformer, you can then step the voltage up and back down, have it delivered at the house at the proper voltage, but transmit it at a much higher voltage and be able to send it to much farther distances with less loss and less diameter wire, making it more economical. Well, Edison didn't like this, and he started a campaign against AC current, saying it was very dangerous. And out of it, he started using AC, and he created the electric chair, and he also was electrocuting animals and showing that it would kill animals very easily. And so it was a big campaign to try to push away the AC because he had invested all his energy into the DC system. So when it came right down to it, and they, after a lot of hoo-ha and press and attention to what was going to win out, DC or AC for the Chicago World's Fair, it was Tesla that came out on top. And now, 100 years later, we're still transmitting most of our electricity by AC. And DC has its place, but not in transmission. But the funny thing is that DC, when you look at solid state circuitry and you look at all the electronics, computers, cell phones, you look at a lot of our current technology is now DC. So what we're doing in most situations is we're taking that AC current and we're converting it back to DC, and that's what we use in a lot of our solid state equipment. So maybe we'll see a change, because the other thing they've been experimenting with on high tension, long distance transmission, that very high voltage DC might be the way of the future, and it could actually trump AC after all. So what I've come up with is the concept of using basically the PV system, which is mounted on the roof, to provide DC power to electrical element for a water heater. This element is nothing special. It's just an AC element. It's a 3,500 watt element, and it will be installed in the bottom of the water tank in the apartment here on location. The top element will remain AC current from the grid. So it would be technically a hybrid system. Anytime the bottom DC element is not able to meet the demand of the hot water use, the top element, the AC element, will come on and provide the extra heat to bring the water up to temperature. This is conceptual, so we will see how well it works. One thing to go back, why would I even think of doing this with electricity versus a thermal hot water heating system? That would be solar on a roof in Alaska. Well, think about it. First of all, we have cold temperatures up here. We have freezing temperatures. You're circulating fluids up through the roof. You're freezing, you're thawing. You have pumps running. You have a lot more moving parts with a thermal system. Now, some thermal systems, even in Fairbanks, have been using evacuated tubes. They're working well, but they come at a cost, and there are a lot more moving parts and more technology involved. With this system, it's pretty simple. We're just going to be putting electricity into this element. We've got a couple tricks along the way that is going to maximize the output of this, but essentially, this is nothing but resistance. And with resistance, to explain resistance heating, you could think of it as almost friction. And when you're dragging something across something else, you are creating heat. And that's all a thermal element like this does. It's no different than the electric heater that you might plug in into the wall. I mean, it's working on the same principle. What I'd like to do now is I'd like to explain to you what a BTU is and how it relates to this PV system and kilowatts of electricity. Okay, so I'd like to talk a bit about electricity and how it is calculated into wattage. So basically, wattage is power. That sounds kind of political, doesn't it? Wattage is power. Power equals volts times amps. A volt, thanks to an Italian named Volta, who was also the inventor of the first chemical battery, which essentially was layers of layers of fabric soaked in salt water and then different metals creating a current, and actually made electricity back in the 1700s. But so a volt times an amp equals watts. Watts are basically what we get charged for when we, okay, there we go. Watt times time equals kilowatt. A kilowatt is 1,000 watts. A kilowatt hour is 1,000 watts over an hour's period of time, times 1 hour. A kilowatt hour is what we are used to when we pay our electric bill. We pay, in Anchorage, we pay 20 cents for every kilowatt hour we use. So if you think of this system here, this is my amp meter hooked up to the photovoltaic panel array. I've got 8.3 amps. If we take 8.3 amps times what is right now around 110 volts, 110 volts over the period of time, if we multiply that out, what did we say? 940 volts. No, watts. So that's almost a kilowatt hour of electricity. We know that 1,000 watts would make our 3,400 BTUs. So we are making heat right now. It's a fairly cloudy day, but we're still able to almost make that 1,000 watts of electricity to give us that 3,000 BTUs. If you think about how electricity is broken down in the household, we probably, with our water heater, we're probably looking at about 30% of our electric bill being the electric water heater, if you have electric water heater in your house. That 30%, depending on what your bill, if your bill's around $100 a month, you're probably looking at a $30 to $40 a month amount for that hot water. The average household, they're saying, is using 20, 25 kilowatt hours per day. This household is a single person. He's down more around 12 kilowatt hours per day. But I know that water heater is using 3 to 4 kilowatt hours per day. Thinking about it from an energy conservation standpoint, we know that if we can address that hot water heater both in the water usage and also in the temperature of the delivery, and if we can supplement it with solar, we are going to affect the bill, and that will be one of the sort of things that we'll be looking at in the future to see how cost effective this is. So if we were to look at a BTU, 1 BTU is the energy it takes to raise 1 pound of water, H2O, up 1 degree Fahrenheit. So if we look at water, we know water weighs approximately 8 pounds. So if 1 pound of water, so if we figure out that we've got 8 pounds, if we multiply 8 times 1, of course, we got 8 BTUs per gallon. If we figure that this is a 30-gallon tank sitting inside the house, 30 gallons times 8 for the 8 BTUs per gallon is going to equal, what, 240. So now we got 240 BTUs for every degree that we want to raise that temperature. 240 BTUs per degree. So if we take that and we multiply it, say our water, let's say our water's coming in at 50 degrees, and then we're going to raise that water, say, to 110 degrees. That's going to give us a delta T, a difference of temperature of 60 degrees. So if we take that 60 degrees and that the delta T, and we multiply it times that 240 BTUs, that's going to tell us how many BTUs we're going to need from that electric element to heat that water up to, say, that 110 degrees. So if you do the math, 240 times 60, if I'm not mistaken, comes in around 14,600. That amount, if we divided, we figure we're putting out, say, 1,000 watts per hour with our PV system at a good capacity, charging that element. If we divided that out by, say, if we got 1,000 watts, that means, and for every 1,000 watts of electricity equals, we'll say 3,400 BTUs. It's 3,413, but that's where if we divided that 14,600 by 3,400, we're talking maybe 4 or 5 hours to heat that water up to our delivery temperature. Now that 4 to 5 hours is under good conditions, but what's that telling us is that if we had a good day of sun, by the end of the day, you're going to be able to have a 30-gallon shower or bath with 110 degree water. So for all practical purposes, our system should work. So basically, looking at the bottom element more as the preheater, with a typical water heater, the cold comes in and goes to the bottom of the tank. So that's where the cold water's coming in. being preheated by the bottom element. This is the temperature probe right here that is going into next to the water heater, and that's what's regulating, the temperature to turn on or off, and it's set at like 160 degrees. So there is the new element, 3500 watt, 240 volt AC element that was supposedly the best match. This is just the power coming in and out, positive, negative, and everything from the AC has been disconnected and capped off. So there is no power from the AC coming to the bottom. It's all up at the top. The top element up here I have set at 130 degrees so that it will give always the assurance that you'll have a good delivery temperature if you're going to be using hot water for showering or the sink, etc. Now this is a charge controller specifically designed for hot water heating, and MPPT basically stands for maximum power point tracking. Essentially it's an optimizer for taking the power from the PV system, which can vary according to the sun, if you've got clouds, temperature, and converting it to the optimum amperage voltage rate to put the watts into the resistance heater, in the water heater. So far it seems to be working pretty well. I can cycle through and check for temperature. Right now it is in Celsius. 46.5 is the temperature that is in the bottom of the water tank. That equates to around 115, 120 degrees. So it's almost perfect right now for using for, say, a shower or a bath. I've also included a breaker between it and the hot water heater, just as a safety, and that's essentially just a DC breaker. This is incoming from the panels, positive, negative, feeds into our controller, and then feeds down and on into the water heater. So far, it seems to be working pretty well. We'll see how it makes it through the summer, and we'll be able to look at, again, utility bills, etc., to see its real performance. So one thing I'm doing is monitoring using this Emporia View. It's set up on the breaker panel, and I've got one hookup going right to the hot water heater AC breaker. So on the View app, if we look at the graph, we see that basically we've got 3 days of data there. The first day, low kilowatt hour draw based on the fact there was no showering. The next day there was bathing and showering, and then the next day was when the solar was actually hooked up and there was showering that happened. So that gives us an idea of what it was before without a shower, what it was with a shower, and then what it was with the PV and a shower. So quite a dramatic difference, and that might be an early indicator that the element is actually doing something. Okay, so what I got here is probably the most basic hot water system using PV you're ever going to see. It's good for demonstration purposes. We've got a 5-gallon bucket, which we will put our 12-volt DC element in. It draws 600 watts. We'll hook it up to our panel and we'll make hot water. We'll see what kind of temperature rise we get with a little thermometer. The one thing I will be missing is a spigot, but you can always use the bucket just as if you used any other bucket. And so essentially, to assemble this, first thing I'm going to want to do is put a hole in it. So probably got it too much of a drill to do what we're doing, but it'll work. There's our hole, just like that. It's kind of like a cooking show, you know. We're going to cook up some hot water here. Here's a special fitting, which I should have the other part of, hopefully. And it's just a through fitting that will then lock in here like such. We put our through the hole and we get our connection. Let's see, I think I want to go like this. They do say tighten with an arrow the opposite way that I'm going. So like such, seals on the inside of the bucket. Okay. And here's our element, 600 watt DC. And it looks like it threads just like everything else. Tighten that up. Missouri Solar sells these 12 volt 600 watt elements. You can order them online for about $20. So there. Next thing we want to do is put some connectors onto our wires that then will then hook to our solar panel. Crimp these connectors. Okay. So then we're just going to hook these to our two terminals of our element. Of course, you could get more sophisticated, but we wouldn't be able to put this together in 5 minutes. But this will give you the basic idea of how the DC element works off the PV. One thing, you never want an element, a water element, to be dry. You will burn out an element if it's not submerged in water. So you always want to make sure you have that element covered with water before you try such things as I'm trying. See, maybe I drill a hole for the thermometer to go through. Use the overkill on the drill, but hey. Okay, so I think now I'm just going to go fill it with water. Five gallons of water. Put our lid on. I think water was a little warm in the hose, so it gave us some solar gain already, just thermal solar gain. 62 degrees, 64 degrees. So we'll hook these. The good thing with these is you can't hook them the wrong way because there's only one way they'll hook up together. There's one connected, and there's the other one. So at this point, we should be having electricity going to our element. Test right now to see how many amps we're driving out of our PV panel into the Hillbilly Solar water heater. 12 volts. So 8 amps at 12 volts. If we do the math, it's about 100 watts. It's not a huge amount, but we've gotten near the end of the day. There's not a whole lot of sun, but we still are producing some electricity, 100 watts. So there you go. There's about as simple and quick as a person could make a water heater. So in conclusion, I've got some takeaway questions that I'm asking myself, and I'll ask everybody that's participated in this. Do you think that PV solar is an appropriate technology for the polar region? Can PV solar be cost effective? on small-scale off-grid installs? Is PV solar a good investment for large multifamily units, multi-use buildings in Alaska? And can PV solar be incorporated into the energy efficiency retrofit program and be cost effective? These are good questions to ponder. From what we could see, we know that PV solar is alive and well in the north, in the polar regions. We've seen it many installations. You see it at all the parks up here. You see it along the highway. You see it on the railroad for switching devices. You see it on electronics, cell towers. It is a good way to provide power on off-grid situations, often done with a hybrid system using wind. On small-scale off-grid, it's the way of the world up here. If you're off the grid and you're living in a homestead lifestyle off in somewhere on a homestead property far away from power lines, many people rely on the PV solar to take care of their basic needs. And we've seen a lot of application here in Anchorage with the Housing Authority, and on all their buildings they've got major PV solar installs, and they're proven to be cost effective. Our little hot water heater system, we did the calculation and we're figuring, well, it's going to have a 4-year payback. That's not a bad payback, a savings to investment ratio. That fits well within most of our parameters. And could it be used, say, in the weatherization program? Could we see more of this technology being used, say, on small single-family homes out in the rural areas of Alaska, or even on multifamily buildings on the roof, and everybody is benefiting from it? I think there's potential there. Whether it's just being used to heat hot water, or it's net metered on the grid, off-grid, hybrid, there's many ways to so-called skin the cat. But I do think it makes sense, and I do think we're going to continue to see it grow up here, and I think we're also going to continue to see the technology improve. Again, as we've said before, the cost of generating electricity with PV has come down tremendously in the last 20 years, and we'll see more and more support, hopefully, for the continued growth using PV solar. But in closing, I'd like to take a moment to thank everyone that's been a part of this production and who's also participated in viewing this production. It's a new world now with our virtual conferencing and trying to get the word out on a topic that, in my mind, is very important. And I see a lot of benefit in being able to do on location and filming in the field and actually showing real life work that's happening. So we do have that as a takeaway. We do have that as a benefit of this sort of approach. I know for everybody that might have participated in a hands-on experiment or a demo in a classroom setting, it's a little different, but you can go ahead and do your research and get in your backyard and put together your own solar system if you care to. I mean, I can't say I was an expert when I started, and I can't say I'm an expert now, but I have learned a lot just by getting my hands dirty and doing the work. So I encourage everybody to do the same, and good luck. Thank you.